While the production is running, during that same day, you should be able to teach, for example, a new welding batch or a new pick and place batch offline, thus offline programming. This component doesn't exist anymore. So you go to CADENAS library, try to find the exact same component or close to it. You test it in simulation, does it fit still, robot doesn't collide, and so on, and you continue. So you have a direct access from the simulation tool to 3D find it, and you can drag and drop a 3D model to simulation world. But we are at the stage that the PLC, for example, doesn't know, is it a real machine or is it a digital machine? Then it is a digital twin. But when we start to pour in data, we move in the gradient towards the digital twin. My name is Jarkko Soikkeli. I'm from Visual Components, and today I will be talking about again, digital twins, but slightly different angle. So the Visual Components is a software company, and we have worked 25 years on developing simulation softwares for the production industry of different sizes and types. From really small companies who want to test their robot cell, all the way to like a really big scale manufacturing plants of Samsung or Toyota or practically whatever. So they have a slightly different perspective on what is a digital twin when we talk about the production, not an individual component or machine. So as you know, when something new is planned, is it a new machine? Is it a robot? Is it a manufacturing plant? You have more or less the same pathway. You start by having a really quick sketches. And believe or not, I have seen a manufacturing plant sketches drawn on the other side of the hotel receipt. Not necessarily the best way, but works. So there are tools, for example, the Visual Components and many other tools, to design first your concept, and then when you have a common agreement kind of what the concept is, then you start to study it. Will it work? So we pour in more information to the simulation model in this case. Okay, now we have studied it, that okay, it works. Then we tested it against real life. So we start to connect it to the PLCs, robot controllers, or other digital twins, other softwares, until the plant is in production, for example. And then you have the execution time of work. So from concept to more concrete plan to commission phase, and then you have actually the system running. And on a concept phase, it's about communication. So this is our software running. So from our library of parametric components, for example, a conveyor, it doesn't matter whose conveyor it is. Conveyor is a conveyor. It has length, width, height, speed, acceleration, deceleration, and all of that has a parameter to it. So from the library, you create the very first idea how the layout may look like. And if you have a 3D environment, that is not brand specific. For example, there are like 40 or 50 different robot brands alone in our library. And you build your idea, and all of the components have enough information inside that they know who they are, so they know how to move in a principle, how to pick and place a product and so on. And then you can create your communication material, VR environments, 2D drawings, whatever you want to show. So this part is the communication, to convey your idea forward, so that there is no like an misinformation or the other guy understands a concept wrong way and so on. This is time saving. Okay, we have a plan. So then we need to actually test, does it work? We need to analyze the system. Most of the time your plan doesn't work, unfortunately. So there are details that you need to change. Okay, robot doesn't reach. that machine is too slow. That component doesn't fit if we go to more on the CAD level. So, the same layout, but we start to introduce real products, CAD models. We create, for example, assemblies from those for palletization. We define value-adding processes. For example, there is a human operation in that process. We define a flow of products, how the products move through the production, in which time or how, in this case with mobile robots. And then of course mobile robots will utilize their own capabilities to move the product from process to another. And then we start to optimization after the basic flow works. In this super simple example, we just tested what kind of a capacity that simple spiral conveyor needs to have. Or, for example, we have a fleet of AGVs. What if we increase the amount of AGVs? And now we can see that the utilization starts to be in a better level. Simple things, but you need to test. Or robots. Do they reach? Do they collide? How to make several robots work in the same pace. And after you have tested, you will get the actual cycle time. So if one robot does a task in 10 seconds, and you have multiple robots in the same pace, for example 4 robots, not all of the robots are doing the same task in 10 seconds because they need to wait the other guy moving. And calculating something like that on a paper is not possible, or it's super complex. Okay, we have our plan, we have a good layout, we have proven it works. Now we actually start to build it. So in this stage, the same layout, using the same tool, we start to validate the whole layout or the critical components of it, either or. In case of robots, we connect it to the real robot controller. In case of machinery, for example, the Beckhoff in this case, we connect the simulation model, for example, through OPC UA to real controller. Now we are testing the PLC program. But still, you don't need to have the real hardware on the other side. Thus the name digital twin. So practically the points before this level, I like to call digital model. We have a digital model of this component in a CAD world. We may have a digital shadow of a machine that is following the orders of a real PLC, of real robot controller, but it doesn't give any feedback back to the simulation or the model. I will come back to that later on. And then when we have the commission done, we have actually the operation phase. So early days, you bought a conveyor from this operator, robots from that provider, PLCs from here, you build your layout, and then you produce the exactly same product for 5 years. That's not happening today anymore. I have seen a production system that changed the product they produce every day. Because they produce, for example, a certain type of a mobile phone. For example, 20,000 units. They produce it in a day. And then they change the model. So you need to be able, while operating, for example, you need to teach the robots again and again and again, or processes, PLCs, change those. While the production is running, during that same day, you should be able to teach, for example, a new welding batch, or a new pick-and-place batch, offline, thus offline programming. So it is continuous work that you are doing. So This is the whole flow, but also why we are here. So how the CADENAS kind of steps in. All of these steps require data. They require your plan, 2D drawing, CAD models, whatever it is. In case of concept design, we have some static components that you can find from, for example, CADENAS library. When we go into more detailed plan, I will show a better example of this. From the library, for example, we can get an Festo or Shunk gripper into our robot. Even though the robot is already in our library, not all of the different smaller components are. It's borderline impossible. So CADENAS is one source. When we go to commission, practically the size of parts is getting smaller and smaller and smaller. So we start to put actually sensors, linear units, actuators into simulation model. And then, as mentioned, the production changes all the time. Or we need to maintain the automation cell. So you start to change the components. This component doesn't exist anymore. So you go to CADENAS library, try to find the exact same component or close to it. You test it in simulation, does it fit still? Robot doesn't collide, and so on. And you continue. So for example, inside our simulation tool, you can open 3D Find It. And you have seen this yesterday and today so many times already that you know how this thing works. So you have a direct access from the simulation tool to 3D Find It, and you can drag and drop a 3D model to simulation world. Unfortunately, at least not yet, the models does not necessarily contain axis information. Or, for example, electric connection information, or logics, or anything like that. But we are getting there. In the same way, if there would be AAS models that are more refined than just a CAD model, for example, we could utilize those directly. But for now, luckily, we can still do it. So, in this example, we have a really simple robot cell, super simple robot cell. It's built from components in the library that you can see on the left side hand of the screen. So from the library we have taken conveyors, we have taken a simple CNC machine or lathe. We have taken a pedestal and a robot, no tool. And then of course the robot tool is selected based on the product that you would like to handle. So in this case, we can go to the library of our own. There are, I don't know, 3,000 to 4,000 components, all of parametric components already there. But of course, it's never complete. You get most of the stuff there, but not everything. So instead of that, go to Find It and start to propose, for example, a mechanical gripper. In this case, it was Festo. So Festo's mechanical two-finger gripper. And as mentioned, it doesn't yet contain the axes of freedom or the hierarchical structure of the component. Oh, sorry, the hierarchical structure is, but it doesn't have, for example, the speed of a joint or the direction of a joint, how the fingers move. But that information, as you have seen yesterday and today, the AAS, the development of CADENAS, everything is going to that direction, that the model itself already carries enough information to know who he is, how he behaves, how he is controlled, what the limitations are, what the weight is, which is surprisingly important in simulation. But in this stage, we have just a simple CAD model. You cannot connect it yet into the robot, but we have developed a lot of different tools how to do it borderline automatically. So first thing is that you need to define its origin. So practically, in this case, a mount plate for the robot, where you are connecting the gripper in a robot. Then because the hierarchical structure is there, but not the joint information yet. So in this case, we will select one of the fingers, we separate it to a different moving node, and then we define it that, okay, it is a moving axis, it is run with a servo, practically a servo, it has its own axes of freedom, it has a speed, acceleration, deceleration, lag, settle time. And again, now this information is something that you need to dig in from the Festos page. But if the component itself would know it automatically, for example, in any format, we could of course read it automatically here. But now we created a finger, and of course the other side is the follower of the first movement. And now we have our gripper with the moving fingers. In addition to this, in this case, we run a small wizard that will add the electrical connection, like an interface to the component. And from that point forward, you can use it as a simulation component that you already saw in a library on the left-hand side of our tool. So you can save it to your own library. We have many customers who have automated this. So they have, for example, imported the whole Festo library from CADENAS, and because our software has an open API, they have created their own little tool that converts all of those automatically to their own library in simulation side. And then they have Festo grippers. But now we have the gripper there, and we have our wizard from where you can select, okay, what is the TCP point, what kind of input-output signals, so practically IOs you have, is the fingers currently open or close, and then you can just click apply, and it will do all of the magic behind the component, so that you can use it as a simulation object. Let's see, this is a tad slow video, to my liking at least. Okay, come, connect it. Put it in there. No. Shouldn't take that long. Okay, now he's doing it. So it will pair it automatically. And at this stage, simulation already knows that he's a gripper. It has its own, I don't know, do you know robotics, but it has its own tool center point already. So how, when you move the tool center point, what is the position where the, hopefully no one was underneath it, so that it knows from which surface or how the product is picked with this specific gripper. And now you can actually play simulation, and the model is using this new gripper to pick up the part, of course that is a CAD model itself, put it into a machine that is currently practically just a process time. And then it is after the process, it is picked out and put into a conveyor. But these, let's say, unnecessary steps between, those are getting like less and less and less. And that's the goal. So, the digital twin, or the digital world, or Industry 4.0, or whatever the recent buzzword happens to be. So, this is a slide from Jeff Winter. And this is something that we like to use. So, we move from a digital model to shadow to twin, depending on how the information is passed back and forth. So this is something that we talked already. In a production lifecycle, we have a concept, we have engineering phase, we have a commission and actual operation. In digital manufacturing, in simulation, in planning, we have the steps that we went through already. We have the conceptual design, we have a simulation and analysis, we have a virtual commissioning, and then we have the actual runtime. And in here we go from digital model, at least in our minds. This is just a digital model of something real. But when we start to add the connections to other softwares, PLCs, whatever it is, we start to talk about digital shadow. Until, for example, we are at the stage that the PLC, for example, doesn't know, is it a real machine or is it a digital machine? Then it is a digital twin. In my books, CAD model, how fancy the CAD model is not a digital twin. It doesn't have anything to do with it. I would like to say it's a digital model of something real. But when we start to pour in data, we move in a gradient towards the digital twin. Why? This is something, for example, when I'm lecturing, this is actually from Omniverse, so one type of a digital environment. When I'm lecturing or, for example, talking with the EduSide people, I quite often, for example, from students, I asked that why companies bother? Why we are talking about this? Why we do simulation? Why we create digital twins? And of course, the answers are everywhere. So we want to optimize production, we want to produce more, blah, 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 blah. So they are all correct. But unfortunately, companies don't do anything if they don't gain profit out from it. They just don't. It's blunt, I know. But of course, the reasons how to get this, there are many. And the biggest thing is to avoid risks and save time. Those are the big ones. Plan before you implement, one way or another. Then, of course, you want to optimize your production. You want to have an as quick machine or production as you can. You don't want to produce waste. The production needs to be flexible, adaptive. And this is a sentence, I don't remember exactly from where it is, but the present day manufacturing is volatile, it's complex, it's changing all the time. And for the last sentence, it's data driven. And that's what we have talking yesterday and today in every presentation. It's data in different formats, saved in different ways. It's data. And if you don't remember anything from this presentation, you most likely remember this, so I apologize already. There is a saying in simulation, shit in, shit out. You put wrong information in, you are guaranteed to get wrong information out. So if any object, is it an AAS, it is a CADENAS model, whatever it is, if it contains data already verified by the manufacturer itself, then it's easier in other tools to trust the data and you get the correct information out.